Hello friends, welcome back to my YouTube channel. Welcome to uh, the fifth part of my discussion on adsorption, and in this I will continue my discussion on adsorption isotherms. In part number 4, I had started the discussion on this topic. In the previous part, that is part number 4, I had discussed the simplest adsorption isotherm, and today in part number 5, I will be discussing the Langmuir adsorption isotherm. So at the end of this discussion, you will know everything about the Langmuir adsorption isotherm. So let us start the discussion. To begin with, let us understand adsorption isotherms. What are these adsorption isotherms? So if you have seen my video on representation of adsorption equilibria, you must have understood what are these adsorption isotherms. But still, I'll tell you, adsorption isotherms, these are the curves that represent or that describe adsorption equilibria. And since you have this word isotherm, that means the temperature is kept constant in this representation. So in adsorption isotherms, they are obtained by plotting Ca against Cs by keeping T constant. So let me just tell you what are these parameters Ca, Cs and T. I have already discussed this in my previous video, but still I will tell you. Suppose this is an adsorbate and it is contacted with a gas mixture, let us say mixture of A and B. So this yellow molecules, these are B molecules, whereas this blue molecules, these are molecules of component A. So this is basically a mixture of A and B, and it is contacted with a suitable adsorbent, such as adsorbent which can preferentially concentrate molecules of A on its surface. So due to this, what will happen? Molecules of A will get adsorbed on the surface of the adsorbent. So now you have A in the original mixture. Let us say that it is a gas mixture, and you also have A on the surface of the adsorbent. So concentration of A in the gas mixture, in the fluid mixture, that is nothing but Ca, whereas concentration of A on the surface of the adsorbent, it is Cs, and temperature is kept constant. So when you plot Ca against Cs at constant temperature, you get a curve, and that curve is called adsorption isotherm. So it describes adsorption equilibria. It is one of the way of representing adsorption equilibria. It is the commonest way of representing adsorption equilibria. So I hope this is clear to you. I have discussed all this in detail in my previous videos. I am giving link to the playlist which has all my videos on adsorption in the description section. You please watch those videos. So by plotting Ca against Cs, by keeping T constant, you get a curve, and that curve is called adsorption isotherm. So in this case, Ca is plotted on the y-axis and Cs is plotted on the x-axis, and you are going to get a curve, and this is nothing but the adsorption isotherm. This is nothing but the adsorption isotherm. Okay, so the resulting curve, as I said, it is called the adsorption isotherm. And this is the commonest way of representing adsorption equilibria, I told you just now. Then different adsorbents will have different adsorption isotherms on the same adsorbent. For example, if you have two adsorbents, let us say adsorbent number 1 and adsorbent number 2. And if they are adsorbing on the same adsorbent, then A will give a different adsorption isotherm, and component 1 will give a different adsorption isotherm, whereas component 2 will give a different adsorption isotherm. So that's why I'm saying different adsorbents will give different adsorption isotherms on the same adsorbent. The other thing is also true. What is that? The same adsorbent will give different adsorption isotherms on different adsorbents. For example, let us say that you have two different adsorbent. One I am representing it with a red color, and the other one I am representing it with a yellow color. And we are concerned with adsorption of component A. So component A will be adsorbing in a different way on this adsorbent, and it will be adsorbing in a different way on the other adsorbent. And it will give different adsorption isotherms for these two adsorbents, adsorbent number 1 and adsorbent number 2. So the point is, the same adsorbent will give different adsorption isotherms on different adsorbents. So I hope now it is clear to you what is an adsorption isotherm, how to obtain it, what is the significance of that adsorption isotherm. Okay, so let us move ahead. There are many adsorption isotherms. First is the simplest one, which I had discussed in my previous video. The simplest adsorption isotherm I had discussed. This is applicable to those cases where the adsorption mechanism is very simple, and such simple cases are very rare. Very few systems are simple. So you can apply this simplest adsorption isotherm only to such few simple systems. So the simplest adsorption isotherm, it is applicable to those cases where adsorption mechanism is very simple, and very few systems are simple. I have discussed this in my previous video. Then the commonly used adsorption isotherms, you have the Langmuir adsorption isotherm, which I will be discussing in this video. And then you have Brunner, Emmett, Taylor, that is BET adsorption isotherm, which I will be discussing in my next video. Then you have Gibbs adsorption isotherm. I will discuss it in my future videos. The Gibbs adsorption isotherm. Now, what can you say about these three adsorption isotherms? These are based on some theories. These are based on theories that have been proposed regarding adsorption. So these are based on various theories, but none is applicable universally. You cannot, none of this is applicable universally. That means if a particular adsorption isotherm is applicable to one case, it may not be applicable to the other case of adsorption. So that's why I'm saying none is applicable universally. And the other important thing that you have to note over here is these three adsorption isotherms, they are applicable to adsorption of gases. So today I will be talking about the Langmuir adsorption isotherm. Then for liquids, you have Freundlich adsorption isotherm, the Freundlich adsorption isotherm. It is not based on any adsorption theory. It is applicable to adsorption of liquids Then other important thing to note for this is it is applicable over a small concentration range. So you can apply this only over a small concentration range, and it is applicable for dilute solutions. So if you have to talk about Freundlich adsorption isotherm, it is not based on any theory of adsorption. It is applicable to adsorption of liquids. It is applicable over a small concentration range, and it is applicable for dilute solutions. So today, let us know more about the Langmuir adsorption isotherm, which is applicable to adsorption of gases. So let us continue the discussion. Now let us talk about the Langmuir adsorption isotherm. So this is applicable for adsorption of a component from a gas mixture. So this isotherm is applicable to adsorption of gases. So it is applicable to adsorption of a component from a gas mixture. The gas mixture here we are talking about, the gas mixture has a high concentration of that component. So we are talking about a gas mixture which has a high concentration of the component that is to be adsorbed. For example, in order to understand the concept, let us say that we have a gas mixture of A and B, from which only A is adsorbed. So there is a mixture of two components A and B, and out of this only A is getting adsorbed. So in this case, the mixture has a high concentration of A. We are considering such a mixture which has high concentration of A. What is A? The component that will be adsorbed. Then, so Langmuir adsorption isotherm, it is applicable to adsorption of a component from a gas mixture which has its high concentration. Now there are certain assumptions that are made while deriving the equation for the Langmuir adsorption isotherm. Now what are these assumptions? Let us understand. The adsorbed molecules form a monolayer on the surface of the adsorbent. So when there is adsorption on the surface of the adsorbent, then those adsorbing molecules, they will form a monolayer of adsorbent, monolayer of adsorbent molecules on the surface. So this is one assumption, the first assumption. The adsorbed molecules, they form a monolayer on the surface of the adsorbent. The second assumption is there is no interaction between the adjacent molecules on the surface of the adsorbent. So when the molecules come onto the surface, there is no interaction between the molecules. The molecules will not interact among themselves. This is the second assumption. There is no interaction between the adjacent molecules on the surface of the adsorbent. Then the third assumption is molecules adsorbed at fixed sites and do not migrate over the surface. So once a molecule gets adsorbed on the surface, it is not going to move from its place. It will remain at a fixed site. So this is the third assumption. Molecules, they get adsorbed at fixed sites and they do not migrate over the surface of the adsorbent. The molecules do not move over the surface of the adsorbent. This is the third assumption. Then the fourth assumption is the energy of adsorption is same all over the surface. So energy of adsorption, energy associated with adsorption, which may either be released or absorbed, it is same over the entire surface. This is fourth assumption. So the derivation of equation for Langmuir adsorption isotherm, it is based on these four assumptions. The adsorbed molecules form a monolayer on the surface of the adsorbent. The second assumption is there is no interaction between the adjacent molecules on the surface of the adsorbent. Third assumption is molecules adsorb at fixed sites and do not migrate over the surface. And fourth assumption is the energy of adsorption is same all over the surface. So with these assumptions, we are going to get an equation for the Langmuir adsorption isotherm. Okay. Now, in this case, the number of adsorbed molecules, the number of molecules that get adsorbed on the surface, it rapidly increases to a point. So as the adsorption proceeds, what happens? The number of adsorbed molecules, it rapidly increases to a point where further adsorption is hindered due to lack of space on the surface of the adsorbent. So as the adsorption continues, again let us look at the same example. So as the adsorption proceeds, molecules are going to occupy various sites on the surface of the adsorbent. So as this goes on, a stage is reached when, due to this adsorbed molecules, there is hindrance to the adsorption of new molecules on the surface. So that is another important thing that you have to note in this case. So the number of adsorbed molecules rapidly increases to a point where further adsorption is hindered due to lack of space on the surface of the adsorbent. So as the adsorption proceeds, the space gets occupied, and due to this lack of space, it acts as an hindrance to further adsorption. I hope the concept is clear to you. So if you have any doubt, you please mention that in the comment section. So let us understand this with the help of this schematic diagram. So you have the adsorbent, and now it is in contact with a mixture of A and B. A is getting adsorbed on the surface. So it gets adsorbed on the surface, and once it gets adsorbed on the surface, and now a stage is reached when due to lack of space, there is hindrance to further adsorption. So I hope the concept is clear to you. Let us move ahead. Again, we will. So when in the gas mixture, as I said earlier, Ca is the concentration of A in the gas mixture, whereas Cs is its concentration on the surface of the adsorbent at equilibrium. So equilibrium will be reached, and at equilibrium, we are saying that Ca is concentration of A in the fluid mixture, in the gas mixture, and Cs is concentration of A on the surface of the adsorbent. So at this stage, when this happens, the rate of adsorption is proportional to the fraction of empty space available on the surface of the adsorbent. So when equilibrium is reached, when the surface of the adsorbent is covered and there is a lack of space on the surface of the adsorbent, so at this particular stage, the rate of adsorption is proportional to the fraction of empty space that is available on the surface of the adsorbent. And the other parameter is the concentration of A in the gas mixture. So the rate of adsorption is proportional to the fraction of empty space available on the surface of the adsorbent, 1, and 2, it is also proportional to the concentration of A, that is adsorbate in this case, in the gas mixture. So if you have to represent it mathematically, you can represent it in this way. So rate of adsorption, I am denoting it as Ra. So Ra is directly proportional to A naught into Ca. A naught is the fraction of the empty space that is available on the surface of the adsorbent, and Ca is concentration of A in the fluid mixture or in the gas mixture. So if you remove the proportionality, you will have Ra is equal to K naught into A naught into Ca. I am calling it as equation number 1. So in this case, A naught is fraction of the empty space available on the surface of the adsorbent. K naught is a proportionality constant, and that proportionality constant is called velocity constant for adsorption. And Ca, it is concentration of A in the gas mixture. So at equilibrium, you can say you get this equation. Or not at equilibrium, when you are at a stage when there is not enough space on the surface of the adsorbent, at that stage, the rate is directly proportional to the fraction of empty space that is available and to the concentration of A in the gas mixture. So that gives us this equation, Ra is equal to K naught into A naught into Ca, and I am calling it as equation number 1. So let us move it. So as the concentration of the adsorbate on the adsorbent surface increases, what happens? The desorption also starts along with adsorption. So I have in my discussion on adsorption equilibria, I have discussed how equilibrium is reached. So when there is enough concentration of adsorbate on the surface of the adsorbent, the reverse process starts, which is that reverse process desorption. So the desorption also starts along with adsorption. So let us say that you have a monolayer of adsorbed molecules on the surface of the adsorbent, and now there is enough concentration of A on the surface of the adsorbent. Now the reverse process will start. Some of the A molecules, they will get dissolved. So at a constant temperature, if you have to talk about desorption, at a constant temperature, the rate of desorption, it is directly proportional to the fraction of the surface that is occupied by the monolayer of the adsorbate molecules. So in this case, the rate of desorption at constant temperature, it is directly proportional to the fraction of the surface that is occupied by the monolayer of adsorbed molecules. So that is the case with rate of desorption. The rate of desorption is directly proportional to the fraction of the surface occupied by monolayer of adsorbate molecules. So if you have to represent it mathematically, you can represent it like this. Rd, if this is rate of desorption, it is directly proportional to A1. And if you remove the proportionality, you'll have Rd is equal to K1 into A1. And I'm calling this as equation 2. And in equation 2, A1 is nothing but fraction of the surface that is occupied by the monolayer of adsorbate molecules, and K1 is a constant, the proportionality constant, which is called velocity constant for desorption. So for the desorption process, which starts when you have enough concentration of adsorbate molecules on the surface of the adsorbent, the rate of that desorption process is given by equation number 2. Rd is equal to K1 into A1. So I hope the concept is clear to you. If you have any doubts, you please mention them in the comment section. Let us move ahead. So for our adsorption, we got equation 1. What is that equation? It is Ra is equal to K naught into A naught into Ca, equation 1. And then for desorption, we got equation 2. What is that equation? Rd is equal to K1 into A1. So now, when dynamic equilibrium is reached, which happens when these two rates are equal. So at dynamic equilibrium, Ra becomes equal to Rd. Rate of adsorption is equal to rate of desorption. So if you use equation 1 and 2, it will be K naught A naught into Ca is equal to K1 into A1. Let me call it as equation number 3. Now, A1. What is A1? This is fraction of the surface that is occupied by the monolayer of adsorbate molecules. We had understood this just now. Now, and A naught, what is A naught? A naught is the fraction of the empty space that is available before the adsorption takes place. So that means, that is the fraction of the empty space that is available on the surface of the adsorbent. So you have two fractions. One is the fraction of the surface that is occupied, and the other one is the fraction of the surface that is empty. So when you add these two fractions, empty plus occupied, empty fraction of empty space plus fraction of space occupied. So sum of those fractions is equal to 1. So from this I can get I will get A naught is equal to 1 minus A1. 1 minus A1. And then I will use it in equation number 3. So in place of A naught, I am going to replace with 1 minus A1. So if I do that, it will be K naught into 1 minus A1 into CA, that is equal to K1 into A1. If I simplify it, it will be K naught into CA minus K naught into A1 into CA. K naught into CA minus K naught into A1 into CA, that is equal to K1 into A1. That is K naught into CA. If I take this down to this side, it will be K naught into CA is equal to K1 into A1 plus K naught into A1 into CA. And in the next step, I will take A1 common. So I'll get this equation K naught into CA is equal to K1 plus K naught into CA into A1. So that will give me an equation for A1. So A1 will be K naught into CA divided by K naught into CA divided by K1 plus K naught into CA. So at the end of this particular discussion, I get an equation for C1. So let us move ahead. So previously we got equation for A1. What is that equation? A1 is equal to K naught into CA divided by K1 plus K naught into CA. Now what I will do, I will divide with K1, divide the numerator and the denominator at the same time. So it will be A1 is equal to K naught upon K1 into CA divided by K1 upon K1 plus K naught upon K1 into CA. And then I will get this equation. I'll tell you what is B naught. So therefore A naught, from this I will get this equation. A1 is equal to B naught into CA divided by K1 upon K1 is 1 and K naught upon K1 is B naught. K naught upon K1 is B naught. So this is the equation is A1 is equal to B naught into CA divided by 1 plus B naught into CA, and I am calling it as equation number 4. So in this case, B naught is K naught upon K1. You can easily understand that. Now A1, the fraction of the surface that is occupied by the monolayer of adsorbed molecules, it will be defined as CS upon CSM. So what is CS? CS is concentration of A on the surface of the adsorbent. And what is CM? CS, this is adsorbate concentration on the surface of the adsorbent. And CSM, in this case, this is adsorbate concentration on the surface of the adsorbent when monolayer is complete. So when the monolayer gets completed on the surface, so there are two situations. One is you have an incomplete monolayer. Let me show it. So an incomplete monolayer. So at that point, concentration is CS, and when after some time, when the monolayer gets completed, so at that point of time, CSM is the concentration of the adsorbate on the surface of the adsorbent. So I hope this is clear to you. What is CS and CSM? So A1 is CS upon CS. Yep. So if you use this equation for A1 in equation 4, you will be getting CS upon CSM is equal to B naught into CA upon 1 plus B naught into CA, and I will call it as equation number 1. So A1, you need to understand, A1 is fraction of the surface that is occupied by the adsorbate molecules, and CSM is adsorbate concentration on the surface of the adsorbent when the monolayer is complete. So the maximum value for CS is CSM, and the given value divided by maximum value will give us the fraction of the surface that is occupied by the adsorbate molecules. So I hope this is clear to you. So now we have used equation for A1 in equation number 4, and we get equation number 5. So as the Langmuir adsorption isotherm is applicable to adsorption of gases, we can use ideal gas law in our analysis. So we can assume that the gas phase is behaving ideally, and then you can apply ideal gas law. So let us do that next. So previously we got this equation Cs upon Csm is equal to B naught into Ca divided by 1 plus B naught into Ca. I had called that as equation number 5. Now let us apply ideal gas law to gas A that is present in the gas mixture. So it will be Pa into B, that is equal to Na into RT. Pa is partial pressure of A in the gas mixture, V is the volume, Na is number of moles of A in the gas mixture, R is the gas constant, and T is the temperature. So therefore I will get Pa is equal to Na upon V into RT. Moles per unit volume, this is nothing but Ca. So this will be Pa is equal to Ca into RT. That is Ca is equal to Pa upon RT. And now my task is to replace Ca with this equation. So this will be, if I use equation for Ca in equation number 5, that will be Cs upon Csm is equal to B naught upon Pa by RT. Ca is replaced with Pa upon RT divided by 1 plus B naught into Pa by RT. Again, Ca is replaced with Pa by RT. So that is Cs upon Csm is equal to B1 into Pa divided by 1 plus B1 into Pa. I am calling it as equation number 6. And in equation number 6, we have got a new term which is B1. And if you compare equation 6 with the previous equation, you can easily know what is B1. So in this case, B1 is B naught upon RT. So B naught upon RT, we are replacing it with B1. So if B1 into Pa, B1 into Pa, it is very small. So in the denominator, what will happen? 1 plus B1 into Pa is approximately equal to 1. So in that case, Cs upon Csm will be equal to B1 into Pa. So the point is, if B1 into Pa is very small, then in that case, the term in the denominator, 1 plus B1 into Pa, this is very small. So you can assume it to be 0. So in that case, it will be equal to 1. So with this possibility, the denominator becomes 1, and equation number 6 simply gets converted to this form. Cs upon Csm is equal to B1 into Pa. And this is nothing but the simplest adsorption isotherm, which I had discussed in my previous video, where concentration is directly proportional. Concentration on the surface of the adsorbent is directly proportional to concentration in the gas mixture. Csm is a constant and B1 is also constant. So that means in this case, or Cs upon Csm is one way of representing concentration on the surface of the adsorbent. So concentration on the surface of the adsorbent is directly proportional to concentration of the adsorbent in the gas mixture. B1 is constant, and this is nothing but the simplest adsorption isotherm. So that means the Langmuir adsorption isotherm will reduce to the simplest one if this is true. B1 into Pa is very it is less than 1, very less than 1. So I hope the concept is clear to you. So if somebody asks you when can the Langmuir adsorption isotherm become the simplest adsorption isotherm, then you can discuss this. So I hope this is clear to you. So let us move ahead. Okay, so previously we got this equation, Cs upon Csm is equal to B1 into Pa upon 1 plus B1 into Pa. Now I will do some manipulation with this equation. So first I will take reciprocal. So if I do that, it will be Csm upon Cs is equal to 1 plus B1 into Pa upon B1 into Pa. In the next step, I will separate the denominator on the right hand side. So this is CSM upon CS is equal to 1 upon B1 into PA plus 1. In the next step, I will multiply each term in this equation with PA upon CSM in order to get the equation in a proper form. I'm doing this. So if I do that, it will be CSM upon CS into PA upon CSM. That is equal to 1 upon B1 into PA upon CSM plus 1 into PA upon CSM. So what is going to happen in this case now? CSM is going to get cancelled. PA and PA, these are going to get cancelled, and you'll be getting an equation which will be this one. PA upon CS is equal to 1 upon B1 into CSM plus PA upon CSM. So if you look at this equation, or if you just rearrange it, so I'm now just interchanging the position of the terms on the right hand side. So this is PA upon CS is equal to PA upon CSM plus 1 upon B1 into CSM. So the entire term is a constant. I'm calling it as equation 7. And equation 7, which is PA upon CS is equal to PA upon CSM plus 1 upon B1 into CSM. So it is of the form y is equal to mx plus c, where y is PA upon CS, x is PA, the slope is 1 upon CSM, and intercept is 1 upon B1 into CSM. That means if I plot PA on the x-axis and PA upon CS on the y-axis, I'm going to get a straight line whose slope is 1 upon CSM, and the intercept made by the line on the y-axis, it is 1 upon B1 into CSM. So in this way, you can get CSM. If you know the slope of this line, you can get B1 once you know CSM. So this is Langmuir adsorption isotherm. This is Langmuir adsorption isotherm. The line described by this equation is the Langmuir adsorption isotherm. So I hope you must have understood what is Langmuir adsorption isotherm, how to get equation for that, how to plot that Langmuir adsorption isotherm. So with this, I end my discussion for this video, where I have discussed the Langmuir adsorption isotherm. In my next video, I will be discussing the BET adsorption isotherm, Brunner-Emmett-Taylor adsorption isotherm. So for now, I will stop my discussion. Thank you for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. In the description section, there is link to the playlist which has all my videos on adsorption. You please watch all those videos. For now, thank you for being with me. Have a nice day and hope to see you soon in my next video.